Everybody. Dylan Abel here with Windrock. I've got Mike Jones and Brian Blanchard here with me as well, a couple of our SMEs. First, just want to take a minute, kind of thank everybody for joining us today. I know it's tough to just take time out of your day to join a webinar. Hopefully, everybody's able to get something out of this. Next, please just kind of be patient with us. You know, we are working remotely. Just stick with us if we have internet issues or a dog barking in the background or something like that. There is a chat window down at the bottom. If you have questions, please just open up that chat window, type your question, and Mike will answer those questions as fast as he can. Brian's going to be presenting today. We're going to have more webinars in the next week. Next week's coming up. We're going to try to do one per week. Next week's will be a digital services webinar to cover some product innovation and our new remote operations center. More to that to come at the end of this webinar. Last, I just want to thank both Mike and Brian for putting on this webinar. They're going to be the main speakers today. And then one other item, I know last week we had lots of requests to have the webinars in Spanish. So we are looking into that, and we do plan to get that set up by next week's webinar. One quick just safety moment, something we learned about this week. It's called Zoom bombing. It's when an uninvited guest hacks into the meeting and disrupts it. Obviously, we are putting these webinars on social media. They're free to join, so this could very easily happen to us. Zoom is working to increase their security so this doesn't happen. If it were to happen to us during this session, please just go ahead and log off. Just leave the webinar. I will log in from the back end and end the webinar, and we'll get it rescheduled as soon as possible. As I said, my name is Dylan Abel. I've been with Windrock about 8 years now. Worked various positions with online systems, going out doing installs and commissioning. I was tech service manager for a little while, and currently our product manager, looking after our product portfolio and our roadmap moving forward. I'll hand it over to Mike for his intro.
Yeah, don't see me. There I am. Well, that'd crack a camera lens, I'm telling you. Hey guys, good to see you again. I've been around a long time, done a lot of things. Started out as a mechanic for 17 years. I've been doing analysis for about 35. I got 50 years in the industry as of July of this year. And boy, we're here to help you in any way we can, you know, to do whatever you need to do to get the job done. So really great to see you guys. And now the presenter this week and my partner in crime be Brian Blanchard.
Hey guys, how y'all doing? Brian Blanchard out of New Orleans. Been around for a while. Glad to help anybody that needs any help. Got a little bit in engine, compressors, you name it. So anything with the natural gas industry. So glad to be here and glad you guys are here.
Awesome, thanks guys. Quick outline of what all we plan to cover today. I'll go through just a quick company background, who's Apergy, who is Windrock, and just kind of hit all of our products at a high level, and then hand it off to Brian here. He'll go through dynamic pressure, vibration data overview, fault diagnosis, and then we'll have kind of a Q&A session at the end. So who is Apergy? Apergy, it's formerly known as Dover Energy. It was about a quarter of the Dover business. It's comprised of these, 15, 16 companies that you see here. Windrock falls under kind of the digital side of Apergy, along with Kortstein and Norso Wellmark. Apergy is kind of present across the well site, from drilling, downhole monitoring, artificial lift, automation technologies, which is where Windrock plays with its online monitoring systems, and then production equipment. A little bit of Windrock history here. Windrock was kind of a buyout from CSI. CSI is now part of Emerson, but there was this technology for monitoring compressors. CSI didn't really want to move forward with it, so three employees bought out that technology and started Windrock. We now have 4 generations of portable analyzers. Our most newest one is the 6400. You can see it on the screen right here. We have kind of 3 online monitoring systems. We start off with OnGuard, and now we have Platinum, which is our newest real-time monitoring system with protection. And then we have Auto Balance, which can be added to a Platinum system. Auto Balance, what we do is we install automated fuel valves, and the Auto Balance takes the peak firing pressures from the Platinum system, runs an algorithm, and adjusts those valves open or close to keep the engine in equilibrium. Our newest product is Spotlight. We have Spotlight for compressors and then Spotlight for high-speed engines. A little more about our products, kind of starting with Platinum up here at the top. As I mentioned, Platinum is a permanently mounted online system. It incorporates the technology of the portable analyzer, so each channel can be programmed for any sensor type. Platinum does have your shutdowns for the system okay, the warning, and the danger. It is targeted towards your critical assets that are critical to the process. If at any sign of a failure you want that machine to shut down, then that's where Platinum would come into play. Moving over to the portable analyzer, this is kind of Windrock's first product. It's well known throughout the industry. You use it, go out to a compressor engine, manually take that data, hook in your pressure sensors, your accelerometers to it, capture that data, move that data over to a laptop, and then use Windrock MD to run analysis. Newest product down at the bottom is Spotlight. As I mentioned, we have it for both compressors and high-speed engines. This is a remote monitoring product. It's quick and easy install. Currently for say a 4-throw compressor, our guys can go out, unpackage the system, have it installed, up and running, taking data in just a couple hours. Of course, that is pending, working with the customer on getting power to the system. It's low installation cost, low cost system, meant to be spread across entire fleets. Then last is kind of the Windrock Enterprise software. It's our dashboard. From here, if you've got, say, 100 Spotlight systems out in the field, you can see all 100, do fleet benchmarking, or you can drill down into one specific compressor engine for analysis. Most recently, we do have our 6400 Enterprise, so now you can take data with your 6400 portable analyzer and upload that into Enterprise as well. So where are our systems kind of used, where are they targeted for? This is kind of how, after talking to customers, how we see assets being broken up. There's about 20% that are critical. They require that Platinum system. They need those 24/7 protection, shut down at any sign of a high or low alarm. And then 75% of the assets out there are essential. That's where you want to monitor those assets, keep up with them, do your predictive maintenance. But if something were to happen, you've got another asset there that can be started up. So this is where we like to deploy our Spotlight systems. And then the Spotlight system can help raise its hand, say, hey, this compressor has an issue. And then the idea is you would go out with your portable analyzer and do a more in-depth analysis. So I am finished here with the products. I am now going to make Brian the host, and he will start up his presentation. All right, Brian, you should now be the host.
All good?
We're all good. We can see your presentation.
All right, perfect. Hey guys, the beginning of this presentation, half of it's going to be talking about how to collect data, talking about the plots, where to collect data. The second half, I have a bunch of data showing you some engine issues. All right, so what we all should know is that we're gonna take pressure, vibration, and temperature on the engine. These are our three indicators. Most high-speed engines, we can't get pressures, but we will learn about pressures in the first half of this presentation because as an analyst, even though you don't have pressures, you need to understand what's going on inside that cylinder. So if we could take pressures, we take internal cylinder pressures per degree. But also, the main thing we're going to take on high-speed engines is we're going to take a raw vibration and a high-frequency vibration, and that's taken with the accelerometer. And basically, we're looking for mechanical impact with those two frequencies. And mechanical impacts will show up as basically get my laser out here, a sharp spike in our vibration trace, okay? It's a half diamond Moore shape. That's what we're looking for mechanical noise. And then we're going to take an ultrasonic with the ultrasonic probe. It's more of a microphone, and it's going to show up more as a cigar shape, and we're going to mainly look for gas noise with that, like ring leakage or valve leakage. And then if we can get exhaust temperatures, that helps us analyze the combustion. So these are really our three main indicators that we're going to look at. So in our analyzer screen, with a 4-stroke engine, all engines have 4 events. So we have a power, exhaust, intake, and a compression. On a 4-stroke engine, this occurs in 2 revolutions. So you can see down here in the bottom of the screen, the x-axis is 0, which is top dead center, 180 will be bottom, and 360 will be top. And then the second revolution, same thing, 540 will be bottom, and 720 will be top dead center again. So really 720 and 0 is the exact same point. So what's going to happen here, if you notice the pressure trace here, the pressure begins to build right after top dead center, and it pushes the piston down. So the red line is a representation of the piston movement. So you can see here is that top, and as the piston moves down toward bottom dead center, this is bottom dead center. So that is considered the power stroke. So this is the pressure that moves the crankshaft round and round. So somewhere around bottom dead center, our exhaust valve opens. We can see the pressure drop here, and you can see the noise in the vibration trace also. And it's a gas noise because it looks like a little cigar. Now the piston's moving from bottom to top, and we're pushing all the exhaust out. That's considered our exhaust event. And then right here at top dead center, this is considered top dead center exhaust. And our exhaust valve closes, and right before that, our intake valve opens. And now from top to bottom, we're actually pulling in air. So that's our intake stroke. And then at bottom dead center, you can see the large impact here, mechanical impact. That's our intake valve closing. And then bottom dead center to top dead center, all of our valves are closed, and we're compressing air and fuel at this point. And then somewhere around 700 degrees, we have a spark, starts our combustion. And then right here, you can see our combustion takes off. So on a 4-stroke engine, top to bottom, each event shares a stroke. So top to bottom is power, bottom to top is exhaust. So it does share, each one of these individual events shares a stroke. That's unlike a 2-stroke engine. So we'll go through this plot right now, piece by piece. So basically what we have here is, you can see our power cylinder here is at top dead center. We do have spark has occurred right here, and you can see the red. We're starting to get a flame front traveling across the top of the piston face. And you can see the pressure starting to rise as the flame front propagation continues through the cylinder. So this pressure is pushing down the piston, which is turning the crankshaft. So this pressure is rising quite a bit, but we don't want it to rise too fast. If you have too rich of a mixture, it rises too fast, detonation could occur. And then we don't want it to burn too slow. In other words, a lean burn might make it too slow. So you don't have enough fuel, you have too much air, and the flame front, the piston will outrun the flame front actually. So you would have something like a soft fire. So everything has to be right in here for combustion, while pressure to rise to create a peak fine pressure about 15 to 20 degrees after top dead center. And then it'll continue pushing down the piston all the way to bottom dead center. So at this point here, combustion is just about complete. It's not quite down to zero. We don't want this pressure to reach zero pressure here. So we're going to still have about 40, 50 pounds here inside the cylinder when our exhaust valve opens. So this is all positive work. So now you can see our exhaust valve pops open here on our cylinder. And because it didn't drop down to zero, you can see a pressure drop. So maybe we might have 50 pounds of pressure here when our exhaust valve opens, and that drives the pressure out. Now we're flowing from 50 pounds to zero, which is pretty much atmospheric pressure on your exhaust manifold. And another reason why we want to keep pressure here when the exhaust valve opens, an important thing to remember here is that at bottom dead center and top dead center, the piston actually stops moving for several degrees. So really in the middle of the stroke, the piston's moving the fastest, and somewhere around here, the piston really comes to a stop. And we want pressure in that cylinder, so when we open up the valve, we can start get that exhaust and all that burnt gas out of that cylinder when the piston's not even moving. So during our exhaust blowdown here, you can see the pressure dropping, and you can see the noise it makes right here on the vibration. So this is a real important event to catch when you're doing high-speed analysis. Because we don't see the pressure drop and we don't see the peak fine pressure, this tells us a lot about our combustion on a high-speed engine. So if I was to compare this combustion on all 12 cylinders on a 12-cylinder high-speed engine, I would expect them all to be the same size. If I have one that's real low, then I expect my peak fine pressure was low, and by the time I got down here to my exhaust opening, this pressure would be low, and I wouldn't have the pressure drop here. I wouldn't have the noise. So when you're taking vibration and ultrasonic on a high-speed engine, you want to move your probe around to make sure that you see this event in your data. So at this point, the exhaust valve's open, and the piston's going from bottom dead center to top, pushing all the exhaust valve out. So somewhere around 360 or 350 right before our intake valve opens and our exhaust valve closes. So you can see up here, our little scale up here, our intake valve actually open around 300 degrees, and our exhaust valve closes here around 417. So now the piston's at top dead center, and we're moving back to bottom dead center. Our exhaust valve is closed, our intake valve is open, and now we're sucking fresh air into the cylinder until the piston gets down to about 540. And this is where the impact here of our intake valve closing, somewhere around bottom dead center. So that's the end of our intake stroke. And now we're at bottom dead center. We're traveling up to 720. All of our valves are closed. Our rings are sealing. And now we're compressing air and fuel. This particular engine actually has a fuel injected valve, shoots fuel right into the cylinder. So we do see this extra impact. This is our fuel valve closing. And then somewhere around this point, we do have a spark occurs, and you can see the air and fuel is starting to burn around the spark plug. And that's the end of the stroke. And you can see now we're starting to have a little combustion starting here. And at top dead center, right after top dead center, you can see the pressure taking off on us. So this is a typical 4-stroke pressure and vibration trace. We have a combustion event, an exhaust, an intake, and a compression. So this next trace here, you can see this is typically what we're going to see on an engine. If this was a high-speed engine, we wouldn't see the blue pressure trace here. So it's really good to understand the pressure inside of a 4-stroke engine, because you're going to have to imagine this pressure when you're doing analysis on your vibration traces. So the top trace here is the high frequency vibration, and this is from the accelerometer. The orange trace here is your raw vibration. It is from the accelerometer. And the bottom trace here is your ultrasonic, and that data is coming from a ultrasonic probe, which has a microphone in it. So these are the 3 traces that we're going to take on a high-speed engine head. The red trace here is actually the ignition. So some high-speed engines have shielded ignition, so we can't get to the secondary, and then some do have secondary ignition wires we can get to, and we have a clamp, we can click on it, and that helps a lot, and that'll analyze the coil, the wire, and the spark plug. Okay, so we had some questions come in talking about last week. So we put some slides in here on how to find RPM and how to strobe in. So we appreciate those questions. I was able to put these in here. So once we get RPM, we're going to strobe into the engine. So when you're strobing into a 4-stroke engine, you're going to strobe in the top dead center. So your flywheel will have a top dead center mark. And then you're going to go to your pointer and you're going to flash it, and you're just going to move that mark on the flywheel till it lines up with your pointer. Now the analyzer knows where to start the trace at top dead center. But you don't know if you're on the actual power stroke or the exhaust stroke. And we always want to start on a power stroke. So basically you're going to have to look at your vibration traces, or if you have ignition, you're going to look at your ignition. All right, so I'm going to go back one slide here. So in other words, on a 4-stroke engine, we should have 3 events. We should have an exhaust blowdown, which is a gas noise, and then we're going to have 2 mechanical impacts at your exhaust valve closing and your intake valve closing. So what we want to see without the pressure, so we don't want to have the pressure, we want to see these 2 mechanical impacts on the right side of our screen, and we want to see the exhaust blowdown on the left side. If you strobe in and you see the exhaust blowdown on the right side and the 2 mechanical impacts on the left side, then you strobed in to top dead center, but to the exhaust stroke. And that's no big deal, okay? So when you're still on top of the head looking at your vibration data, all you're going to do is go to the analyzer or the encoder, and you're going to hit the A/B shift button. And it'll shift your data right then and there. You don't have to get down. You can just shift it 360 degrees just like that. So we want to make sure that that's correct on the first cylinder that we take data. So we want to analyze on the analyzer, we want to analyze this trace on our first cylinder to make sure we are timed in to top dead center power stroke. Okay, we had a question about, can I use compressor? If I hook up to the compressor and get RPM from the compressor, can I use it to take data on the engine? So absolutely, yes. The crankshaft is the same speed. As long as the crankshaft of the compressor is the same speed as the engine, yes, that's how we do it. So there's 3 methods of getting RPM. Encoder is the preferred method. And the reason why we say it's preferred method is because the encoder will send 360 pulses per revolution to your analyzer, which gives us good resolution. If we use a mag pickup or an optical eye, which is fine to do on high-speed engines also, we can use all 3 on high-speed engines. It'll give us 1 pulse per revolution, and then the analyzer will have to figure out the 360 degrees. So on a high-speed engine, we can use the 3. On a slow-speed engine, like 250, 300 RPMs, we always recommend to use the encoder, because the shaft speed can change within 1 revolution. There is another option using the mag pickup on a flywheel gear ring. That'll give us a little better resolution, but if you do that, you're going to have 2 encoders, one counting the teeth on the gear ring, and the other is going to be a top dead center pickup. So you're going to have a hole anyway as a reference point. So you're going to have 2 mag pickups if you prefer this. Okay, so this is the encoder here on the back of, it looks like an aerial compressor. So this bracket here is a Windrock bracket. It's the aerial bracket. You can buy it from Windrock, and it's a great tool to have. Actually, I mean, I use it all the time. It eliminates the tripod with all the piping down here. Easy to use. All you do is just hook it up into the back of the end here, and you can have a friction drive. So you can have a rubber tip here. You can just shove it right into the middle of the shaft here. So it's driven directly off the compressor shaft. You just push it in, get a little friction, and there's a bolt underneath. You tighten it down. So that's one method. You can also put an Allen bolt into the shaft. There's a little hole drilled into the shaft. It fits a 3/8 Allen bolt. And you want a 1-inch long Allen bolt, nothing longer than that. And if you get a 5/16 Allen socket, you can put it at the end of your shaft. And that way it won't slip. That's guaranteed not to slip. If you have a rubber tip, a little oil can get in there and you can have a little slippage there. But this is a real good bracket here that we can use to hook up the encoder to the end of an aerial compressor. If you're going to use a mag pickup, this is an example of a mag pickup. So we're going to drill a hole in the hub or here in the flywheel, and then we're going to make a bracket. So if you do make a bracket for your encoder pickup, you want to make it sturdy. You don't want to make it out of sheet metal. It's good 1/4-inch plate. Have somebody build it for you if you need to. We need a good sturdy bracket here. So that would be a good example of a mag pickup bracket. Okay, so once we get RPM and once we time in the top dead center, now we can start talking a little bit about sampling data on these engines. So normally pressure is not taken on a high-speed engine, so vibration traces should be taken with high frequency and raw. It will be taken with the accelerometer. High frequency will be VT5, and that's going to be a 6 to 25 frequency range. So the default high frequency range is a VT4, and it's from 4 to 15. So that's good for slow speed engines, but on high speed engines, we switching over. Windrock engineers gave us this new test point here years ago, and we get much better data on high speed engines with a 6 to 25 frequency range. So you want to make sure if you're using 4 to 15 on your high speed engines, you want to make sure you go in and shift everything to VT5 and start using this point. And you're going to go into your sensor point editor. It's setup, software, setup, sensor points. You go to your editor and you can change it from 4 to 15 to 6 to 25. Much better, cleaner pictures here. On the raw vibration, it's a low frequency, 0.5 to 10. That's our VL1. So this is mainly looking for piston type slaps, anything big metal, piston slaps, wrist pin bushing. The VT5 is looking more for valve noise, like valve closures and stuff like that. Raw vibration, we're looking more for like piston slaps. So high-speed engines make different noises, so we have to take 2 separate frequency ranges on vibration here. And the third one's taken with the ultrasonic probe, and it's looking for gas noise again, and it's going to be a real high frequency, 36,000 hertz up to 44. So that's why we want to take all 3 here on a high-speed engine. Okay, so first thing we're going to do is get an RPM off the flywheel. Second thing we're going to do is take vibrations on the head. So again, we're going to take ultrasonic and we're going to take acceleration readings on the head. That's going to be all phase data. This is not spectrum. This is phase to the crankshaft reference. If we have secondary wires, we definitely want to take secondary traces. That tells us a lot about the coil, secondary wire, and the spark plug. And if we can get to the primary, we want to take a primary also. That tells us about our electronic output to our coil. So yeah, absolutely, we want to take ignition secondary and primary if we can get to it. And then exhaust temperatures tells, again, a lot about combustion. So if we have a pyrometer, we can take it. We have an infrared in our analyzer. We can shoot the elbow if it's not water cooled. If you have a water cooled exhaust manifold, all you're going to be getting is water temperature. So a pyrometer is probably the best way to get exhaust temperature. And then if you want to experiment a little more, if you get a turbocharger, a blower, you can take some FFT data on that. You can take main bearing readings if you want to get a little more advanced. And also if you want to check the movement of the frame. If you have a foundation bolt loose, you can do some spectrum. So the Windrock analyzer does have the capability of taking spectrum data also. Okay, so let's talk a little bit about probe placement. Where would we put our accelerometer? Where would we put our ultrasonic? So this here is a Waukesha head. A lot of people will put it on a head nut. You can put it on the top if you don't have any little indentions here. You can put it on the side, the flat. On this particular head, it has a lip right here in the middle, and I put my accelerometer right on this lip. And the reason why I do that is when you're taking vibration here, you're actually right in the middle of all 4 valves. So I have 2 intake valves down here. I have 2 exhaust valves up here. And when I put my accelerometer in the middle of all 4, I get a pretty good trace. If I put the accelerometer up here, I'm closer to my exhaust valves. I might not see my intake as good. So I like this spot. There's also a plug right here. If I don't have a lip here, I'll put it on this plug. I'm still kind of in the middle of the head, getting the good data. My ultrasonic probe, I'll put it maybe on top of the valve cover, and I might take a second ultrasonic on top of the nut here or on a flat. Try to get 2 different ultrasonics. So we can put as many acceleration readings we want on one cylinder. We can put 2, 3 ultrasonics. The main thing here, guys, to remember though is when you find that sweet spot, when you find the spot you're getting good data, if you do it to this cylinder, if you put it here or you put it here, when you go over to this cylinder, you want to make sure you put it in the same spot. Because when we do analysis, we're going to compare the data from one cylinder to the next. These cylinders are identical. And one of the questions we had in the email this week is, how do you tell the amplitude of an engine? Well, each engine has different amplitude signatures. Okay, so we can't say this engine's going to put out more noise than that one. No, different load, different configurations will change our impacts. So the main thing we're going to do is we're going to look at the amplitude from this cylinder and compare it to that cylinder and the next. So it's very important to put the accelerometer in the same spot on the head once you get a good location. Here's the same head, but it's a side view and there's a nice flat spot right here. You can put your accelerometer here as long as you don't have anything blocking it, right? So like this header here might block you out, so you might not be able to get on this spot here all the time. I got another spot here. You can see this particular engine has a secondary wire, so I would definitely take secondary ignition on this particular engine. Some of these Waukesha engines, especially the GLs, all the GLs, you might be able to get to the emissions valve. So this is a fuel line here, pumping fuel into your pre-combustion chamber. And you're going to have like a little check valve in here. This is an aftermarket check valve here. It's got a ball in it. And this is actually Waukesha's check valve. And so these little components click back and forth, letting the fuel in and closing, letting the fuel in and closing. And if you can put your accelerometer on this particular check valve, see here, I'm using a stinger. So I have a stinger. I take my magnet off. I put a stinger on here. I touch this valve and I add a VT5 just for this valve. And what I'm looking for in my analyzer is consistency. So every revolution, I should see a couple of clicking noise and they should be in the same exact spot every revolution. If I see one cylinder and a clicking noise that's bouncing around different locations every revolutions, that means these balls and these checks are getting dirty and they're sticking on you and it's time to clean them. Right, so we can analyze that also if we can get to that emissions valve. Here's another example using a stinger. This is on a Superior engine. These Superior engines have a dimple in the stud. The head stud has a dimple. And I've tried the stinger, pushing it into that dimple, getting real good vibration traces. So in other words, what we want to get is the baseline. We want to get a flat baseline when there's no noise going on, and we want to see the valve closures, right? That's a good vibration trace. When we get a flat baseline and all we see is our gas noise and our 2 mechanical impacts. Here's another example. Took the accelerometer, put it on pliers, took the magnet off, drilled a hole in the pliers, screwed it onto the pliers. On this particular Caterpillar engine, this stud goes right in the middle of all 4 valves. You get a real good trace on the valve impacts here. So basically, we want to make sure you guys are experimenting a little bit with your probes. Experiment, try different things, try to get the best looking picture. Right? We want to get a good, clean picture. We want to see that exhaust blowdown. We want to see those valves closing. Here's a 3500 Caterpillar engine. These heads have nice flat machine surfaces on each side. Real nice to put your magnet on for the accelerometer, put your ultrasonic. Some guys put the ultrasonic in the front here. You also got a nice flat spot if you want to try your accelerometer on the front. You might get a better looking picture. Same thing with the 3600 Caterpillar series. They have some nice machine surfaces on the heads. We can put our accelerometer on the head, or we can put our ultrasonic here. This guy took the dust cover off, and they got a nice flat surface on this stud. This stud goes all the way down to the cylinder. So all the vibrations is traveling through the stud out into my accelerometer probe. So this is another good place to try here on the 3600s, right on top of the stud. Okay, so once we get the data here and we get it into the analyzer, now we can start analyzing the data. Okay, so I mean, basically, now we're going to go start talking about graphs and looking at graphs and what do we want to look for, right? So now we know normal vibration patterns. We're going to have 1 exhaust looking gas noise. We're going to have 2 mechanical impacts. So that's our normal pattern. So now what we want to do is we want to start looking for abnormal things in our patterns. In other words, like the biggest issue we normally see is the valve closures are early or later. Okay, and then if we compare the vibration closing impacts of these valves, we want to make sure that they're the same size, the amplitude. So we want to make sure that we don't see some smaller ones or bigger ones, right? So we know we're only supposed to have 3 impacts. So if we have an added impact, we want to go do our homework and find out why. If one of those 3 impacts is missing, then we got to figure out why it's missing, right? And then the last thing we want to look for is something that's intermittent. In other words, when you hit enter on your analyzer, it's going to save 9 revolutions. It's not going to save 1 revolution. So it's going to save 9 traces. So you want to look at all 9 revolutions to make sure the closing is consistent. The exhaust blowdown is consistent. Okay, we always do this on engines, no matter if it's a slow speed engine, high speed engine, or diesel engine. We always want to look at all the revolutions. So it's early, late, bigger, smaller, added, missing, and intermittent. So we're going to start looking at all this right now with graphs. This is a typical valve train. So you have a camshaft, a roller here on top of your camshaft, push rod, rocker arm. You got a bushing and a pin in this rocker arm. You're going to have your valve. You're going to have a guide that holds that valve stem, and you're going to have your springs to close the valve. And you're going to have a little clearance, usually here on a mechanical running engine, hydraulic engine, you're not going to have this clearance. So somewhere in here, you might have a hydraulic lifter. So you need to know your equipment. You need to know this inside your engine. Do you have hydraulic lifters? Do you don't? Now, these are the things you need to know. Any one of these components starts getting a fault. If this pin and bushing starts wearing on you, push rod tips start wearing on you, the roll of the cam. If the valve guide starts wearing, right, it's extra clearance. All of this, all these issues in this valve train here, any one of these issues will show up in your vibration trace and your ultrasonic trace. That's exactly what we're looking for. So it's not always one or the other. It could be anything in this valve train. Your mechanic's just going to have to go inspect the whole valve train at some point. Okay, one of the big things we find is valve lash. In other words, there's too much clearance between the top of the valve and the rocker arm right here. This little gap increases on us. So anytime we get an increase in clearance like that, that's called loose valve lash, excessive valve lash. So when the cam goes to open the top of this valve here, it's got to take out the slack of that excessive clearance. And when it does, the valve's supposed to open here, and it's going to open late. And now it's going to open the valve, and then the valve will close where this dotted line is, and then it's supposed to close over here. So really, the duration is going to decrease on you here. Any kind of valve lash, you're going to have a decrease in duration. Okay, this is an example of excessive valve lash. This is actually 6 different cylinders. And you can see here, we have, stands out at us, we have 2 loud impacts at exhaust closing, and they're early. So what we said was that it's going to decrease the duration. So the rest of these are pretty quiet. We really don't see it. It's probably hydraulic lifters. We're not seeing it here. But we do see these 2 abnormal impacts. We look over here at the exhaust blowdown here, and this is where the exhaust opens. You can see here the exhaust opens pretty close to this dotted line. This one is opening late, and this one's to the right also. It's opening late, and these other 3s are opening right at the dotted line. So you can see it opens late and it closes early. So excessive lash opens late, closes early. Here's an example here. The camshaft lobe hasn't started opening the valve yet, but right here it's supposed to start opening right here. At this point, it's supposed to start lifting it off the seat. Well, now it's got to take out the clearance. So now it's going to open it later than normal. And now the valve opens here, and we see it right here. It opened a little bit later on this side. And now it starts opening the valve, and you can see the lift of the valve is decreased. In other words, the efficiency of my valve is not really good right here because I'm not opening that valve all the way. Took out slack, so now when I'm at full wide open, it's supposed to be up here opening it, it's not. So now I'm not blowing the exhaust gas out of the cylinder. And then now when I close it, it's going to close early here where it's supposed to close over here. So that's an example of excessive exhaust valve lash. It hurts it in 2 ways. The duration of your exhaust blowdown is less, and the valve doesn't lift as much. So you're really doing harm to the breathing of the cylinder. So you're doing harm to your combustion. You're not getting the proper breathing of that cylinder. Okay, here's another example of excessive exhaust valve lash. You can see here, we had a mechanic here. He actually shut the engine down. Normally he has 50 thousandths clearance on the exhaust valve, and he went ahead and put an extra 15 thousandths just to see what would happen. So the blue trace here is normal at 50 thousandths, and just with 15 thousandths clearance, you can see now it walked to the left, maybe about 10 to 20 degrees. So he just wanted to see how far it's going to walk on 15 thousandths. So that's a good example of excessive exhaust valve lash. Another excessive exhaust valve lash here on a Waukesha, he did the same thing. He was supposed to have 28 thousandths, which is the blue trace, and then he added 40, so he added another 12 thousandths here, lash, and you can see it walked this much on a Waukesha engine. And he also took the intake valve at the same time. So he has 2 intake valves. They're supposed to close at the same time. He said, let me make one close a little bit earlier than the other. He put 8 thousandths on one of the valves. He put an extra, and he let the other valve be normal. So you can see here that one valve is closing normally, and when you added 18 thousandths, it walked to the right on it. So he misaligned the bridge here by 8 thousandths. He probably tightened it up because it walked to the right there. But when you see a double impact like that, and you know you have 2 valves that's supposed to close together, chances are these 2 valves aren't closing exactly at the same time. So that's a couple of examples about excessive exhaust valve lash. Now let's talk about if you don't have enough valve lash, if it's too tight or insufficient valve lash. So insufficient valve lash will do just the opposite. Instead of decreasing the duration, it's going to increase it. So if you have insufficient valve lash, we expect the valve to open early and it's going to close a little bit later on us. And if it doesn't close all the way, and if it doesn't seat during the combustion event, during peak fine pressure, yeah, that hot fire will blow through your valve. And eventually it'll burn it just like a blowtorch. So anytime you see something like that, you want to raise the priority on it. We definitely don't want to burn a valve because it's got insufficient valve lash. So here's an example of insufficient valve lash. Same mechanic, he's supposed to say, I had 50 thousandths clearance normally, that's your blue trace. Then he went in there and he tightened it up. He said, I'm gonna put 40 instead of 50. And you can see by just moving it 10 thousandths tighter, he actually made that closure walk to the right. And you can see the opening is a little bit earlier too. He kind of moved this exhaust blowdown to the right, and the exhaust valve is closing late. So anytime you have a late closing valve, chances are you might have insufficient valve lash. Okay, so here's a couple of examples of late, early, and added and missing events. Okay, so this is cylinder 1, the blue is cylinder 2, 3, 4, 5. So this is 5 different traces. You can see here the top 2 are very normal. Our exhaust blowdown opens on time. We can see our gas noise, and we can see our 2 main vents closing right at the right time. Okay, now here on cylinder number 3, you can see our exhaust blowdowns early. So that's a perfect classic of early event. Okay, and then the exhaust valve opens early because it's too tight, insufficient valve lash. And if you look at the exhaust closing, the event's not there, so that's a missing event. So that's a bad thing. It's very tight. It's not letting that valve slam on that seal. So this is a high priority here when you have a missing event. That's a bad thing. Okay. So we also have some late closing events. If I compare all these cylinders here, they're all pretty much the same, except this one, it's later than normal. So that intake valve would have insufficient valve lash because it's closing late. This particular exhaust valve on this cylinder is closing later than the rest of them. So I'm going to call that's late intake valve. That's really late exhaust valve closure. That's wrong. That's late exhaust valve closure. So both of these I would write up for sure. And if this is late, you can see my exhaust blowdown is early. Okay. And over here to the left, we actually have a added. So we have an added impact here, right? So we're going to have to check that. So anything that's added, we're going to have to do our homework there and figure out what's the deal here. So we have to make sure that's not crosstalk. Sometimes we can pick up noise on these other cylinders and it's coming from these different valves. The noise is just traveling over to our accelerometer and the other cylinders. So we have a tool in the software. If we go to the cursor here, top left here, got a cursor, and we check unphased cursor here, we put that check mark on it, it gives us these little lines here, this little gray lines here. That's one, and this is one right here. So you can take your cursor, put it on top of here and left key click, and you can drag it. So when we drag it on top of this impact that we have a question about, we can see that this line lines up perfectly with this valve closure. So that's the noise here. This is not happening in this cylinder here. This noise is crosstalk from this valve closure. So I'm not going to call this added noise here. I know it's crosstalk, and that's normal. So we won't fool with that, but we have to make sure that this added impact is not crosstalk. We got to verify that first before we make a call on this cylinder. And in this case, we're not going to call it because now we know it's crosstalk. So this is a real powerful tool to try to find crosstalk on power cylinder vibration traces. Okay, here's a trace we put in here. Who's setting your valves? Okay, so basically, we have 1, 2, 3, 4, 5, 6 separate dates here. So on 12/16, our vibration looked real good. Exhaust valve closure was right on the money, and this was right before PM. So they told them to go ahead and PM this unit, and of course the mechanics go up there, take all the valve covers off, they break all the valve lashes loose, they get their feeler gauges, they set them all, they tighten them up, they put it back online. Well, when they put it back online, you notice, this is the day after, you notice that the exhaust valve now is closing early. Okay, so this is a bad thing. So you have to have a competent mechanic and knows how to set these valves. Sometimes you can do more harm when you set the valves during a PM. So sometimes you just want to depend on your analyzer and say, okay, we can skip this PM for a few weeks. Let's let it run, because here you did more harm than good. So a good, competent mechanic is very important. So you can see here, the rest of the dates here for the whole month, it was running early, and really it actually started moving to the left a little more toward the end of the month. So very important to understand that if you had a good vibration trace and you knew they did a PM and now it's wrong, then we might have to say something, right? Okay, so that's it about valve lash issues. That's what we find mostly. Let's talk a little bit about ring or valve leakage. So anytime you have ring or valve leakage, if you look at your pressure trace on a 4-stroke engine, between 180 and 540, that's doing the exhaust and the intake. The pressure is real low here. You got about 0 pounds of pressure on top of the piston. So, and your crankcase pressure is around 0. So we don't expect to see on a vibration trace ring leakage in this area here. We're going to see the rings and valves leak when the pressure in that cylinder starts building. And you can see that on a vibration trace. Doing the compression trace here, you can see doing the compression here. Once it starts building up pressure, you can see the noise starting to increase as the pressure increases. And then here at top dead center, we have combustion takes off, and you can see the noise really increases during the peak fine pressure. So that's very important to understand when you're looking at vibration traces and you don't have pressure data, that you're going to have the highest pressure 15 to 20 degrees after top dead center. All right, so if you don't have pressure, you have to imagine the pressure in your head when you're looking at the vibration traces. And you can see it on all of these traces. Even on the low frequency trace, I see abnormal noise at combustion. So this is classic valve or ring leakage. Over here to the right, if I did have pressure on all the cylinders, you can see here I line up all 8 cylinders, and I can see this one particular cylinder, the compression's low, my peak fine pressure's low. So I know I have an issue here on this cylinder. It's supposed to be balanced and with the rest of my cylinders. So this is an indicator of low compression because of a leak, rings or valves. My peak fine pressure is another indicator. And remember, we said that if you have low peak fine pressure, we expect the pressure at exhaust opening to be low, and we're going to see a smaller exhaust. So you can see here, our exhaust is really low, if not missing completely. So when I compare my exhaust for all these cylinders, I bet you my exhaust is even lower than the rest of them. Okay? So that's why we want to compare all the cylinders, and we want to compare all the revolutions together. So this is an example of vibration data and scaling it. We see a lot of this where we see data where it's scaled here from 10 Gs to 10 Gs, and it's so small, we see the mechanical noise here of the valves closing, but we don't see the exhaust blowdown here. And we don't see any kind of combustion noise here like ring leakage or valve leakage. So we want to scale these scales properly. So as a high-speed analyst, you have to make sure you blow up these scales. So when you blow up the scales, it's going to look like this trace, this pattern here to the right. Blew it up from 10 Gs, and now I got it at 1 G scale. All these impacts here are large, and they overlay in here, but that's no big deal. I know I'm supposed to have that there. But look, now we can see our exhaust blowdowns, and we can see now this extra added noise. That's our valve leak there. So if you look at this one, you can see it a little bit, but here it stands out much better at you. So this is important when you're doing analysis on your vibration traces. You want to make sure everything's scaled properly. Okay, here's another example. This is a Caterpillar engine. This is the even side, 2, 4, 6, 8, 10, 12, 14, 16. This is 8 cylinders. You can see we have added noise here, and that is right after top dead center. That's your combustion, that's your peak fine pressure, making a lot of noise here, and we have no exhaust blowdown. All the rest of my cylinders, I can see exhaust blowdown. Over here, I see doing compression. I see a little bit noise, but the noise gets bigger here at peak fine pressure. So this cylinder did try to light off. So we did see a little bit peak fine pressure, but not enough at exhaust to make any kind of exhaust noise. And then this is a good example of a bigger event. Remember, smaller, bigger. And when I'm comparing all my intake closures, you can see this event is much bigger. So I need to set my valves and check my valve lashes here, check my valve train completely here. Why is this bigger? So I would make a call on that. Okay, so that's comparing cylinder to cylinder. We're going to look at all cylinders together and we want to compare them. That's how we're going to tell if one amplitude is bigger than the other. Okay, and then every engine is going to give out different signatures. So that's why we want to make sure our probe's in the same spot on every one of the heads. And we can see a larger amplitude, that's an issue. Okay, so once we look at all the cylinders together and compare them, now this here is an example of looking at all 9 revolutions on one cylinder. And as an analyst on an engine, you have to do this. This is something you must do. This is cylinder 5 ultrasonic trace. And you can see here, this is the top trace. That's the representative trace that the analyzer will show you first. That's the default trace. And you can see an exhaust blowdown here. And you can see your exhaust valve closing and your intake valve closing. Everything else is perfect. But when I look at all revolutions, you can see the second revolution, the exhaust blowdown is missing. The third revolution, it's there. It's missing. It's there. It's there. It's missing. It's missing. It's there. So this is a cylinder cutting in and out due to something, probably a spark plug problem or a wire problem. So you can see it missed this revolution. It fired, it missed, it fired, it fired, it missed, it missed, it fired, it missed. That's why it's so important to move your probe around on the head to make sure we see this exhaust blowdown. And then we always want to look at the data like this. Now, Windrock just gave us, the engineers just gave us a great tool to do the same thing here. And instead of putting all of our revolutions like this on top of each other and looking at it like this, we have a new tool here. The icon here is this icon at the top on your MD software, and it's called single scans. When you click on it, this drop down here happens. And if you click on overlay single scans, it'll overlay all your revolutions together. And you can see right here, this valve closing, it's normal. Every revolution, the impact is pretty close to the same. But if I come over here and look at the exhaust blowdown, they all firing pretty good here. They're all the same, except maybe 1 or 2 revolutions. I can see that I had a missing event. The missing blowdown here tells me that I had a misfire 1 revolution. So that's the things we're looking for. And if I had a pressure trace, which I do in this particular engine, you can see it fired all these revolutions, but you can see 1 revolution, it didn't really fire. And when it got to the exhaust blowdown, there was no pressure there when the exhaust valve opened, so it didn't make any exhaust blowdown noise. So this is a great tool that the MD software engineers gave us. And as a matter of fact, a lot of you guys asked for this tool and they gave it to us.
Hey Brian, sorry to interrupt here. We're coming up on the top of the hour, so probably need to.
Okay, absolutely, and I'm pretty much finished here. Here's another example of abnormal exhaust valve closures, and when you look at it with the overlay single scans, there it is. Okay, so this is a good tool. Let's use it, right? The last thing I have here is valve recession. You can see here the closure is normal, that's your baseline, and over time it's just going to get wider because it's just getting sucked up into the head. And that's about all I have. If you get this presentation from Dylan, which you better get it, We put some valve train problems in here, so normal, worn rocker arms, clearances, broken valves. This is what you're looking for. So this is a great little outline here, okay? So that's it, Dylan, man. I appreciate you guys for joining us. You got any questions, this is our information here.
Thanks, Brian. I know, see at the bottom, people are wanting us to keep going. Unfortunately, we have to schedule these webinars for a certain amount of time, and it will end on its own. So that's kind of why we have to proactively go ahead and wrap it up. I will take this webinar. We'll edit it. We'll get it sent out through email, get it posted on social media so you guys can download it. We'll do the same thing as last time. It'll be uploaded to YouTube. Thanks for attending. Next week, we're going to do another webinar. It'll be with Sal Yacone, our digital leader, and Pete Flanagan, who's our digital service analyst. It'll be on digital services and product innovations. It'll kind of cover our new ROC and everything that's going on kind of behind the scenes. What kind of data are we bringing in? What do we do with the data? What dashboards, AI, etc. are we using to help out our customers? So thanks everybody for attending, and have a good day.
Thank you, guys.